Good day, stat students. So today we're going to look at section 10.2, and we're going to look at specific problems with regards to looking at and comparing two population means, and that means we're going to be running a two-sample t-test because the two groups were independent of one another. All right. So our first example, an experiment investigated whether cell phone use impairs drivers' reaction times, and so that's our response variable reaction times and using students from the University of Utah. So like this was an actual experiment that was run. So we have 64 college students and from the University of Utah, and then they were randomly assigned. 32 were randomly assigned to the cell phone group, and then 32 were in the control group. And I'll define what the control group was here in a second, what they were doing. So students used a machine that simulated driving situations, and at irregular periods, a target flashed red or green. And so, you know, so here's a student, and a red light would flash, and then they would press a button or press a brake, and that was recorded how long it took for them to do that, and then they did that several times for each student. Okay. And then the control group listened to. Now, what do we normally do in our car? We listen to a radio, or maybe do something like books on tape. Okay. And what did the cell phone group? What were they doing? They were carrying on conversation with someone in a separate room. Okay. All right. So here is output from Minitab, and Minitab is just a different computer program. So you might be using another computer program in a different class. You may not be using StatCrunch. Okay, so we just want you to get used to maybe some other computer programs here and its output. And so at least I want you to, anyways. All right. And so here it looks like cell phone group is population 1, control group population 2. I think I've already told you that it doesn't matter when you're doing this for real. It doesn't matter which one you define as population 1 and population 2. The results are going to be the same in the end. Okay, but once we define a certain population, do not change it. Okay, because it might give you the wrong answer at that point because you might have a sign backwards or something. Okay. So this is all stuff from our sample. Obviously, we don't know what's going on with the entire population, and so what do we have here? We have things like N1, and since this is a mean that's coming from that first group, that would be X bar 1, that would be S1, sample standard deviation from the first group. And obviously this would be N2, okay, X bar 2, okay, and S2. This number down here, this is a pretty important number, and every computer program that's running a two-sample t-test would give it to you. They may not call it the estimate for difference, but it would be pretty obvious what they're trying to tell you in the computer output. That's X bar 1 minus X bar 2. Why is that so important? Because that's the point estimate for our confidence interval. It's also basically the numerator for our test statistic. And so you could take this number minus this number. Remember, this is X bar 2. So you can take those two numbers, subtract, and certainly you would get the 51.5, and the computer has a bunch more decimals saved here, and so it just took it out to 4 decimal places. That's all, because it has all that information saved. Here's a 95% confidence interval for the difference. Oh, it looks like it's entirely positive. That's telling us something, but we'll get to that later. Then these last two lines are all about the hypothesis test. It looks like we ran it where the null hypothesis was equal to 0 versus a greater than sign, so a right tail test. Okay, and this is our test statistic. This 2.63, the t-value, test stat, obviously our p-value, and then our degrees of freedom. Those nasty degrees of freedom. This is basically the big reason why we can't calculate this by hand too easily, because of those nasty degrees of freedom. So the computer calculated it for us. All right. So it says here, test at the 5% significance level whether the mean response time for all cell phone users, population 1, is greater than the mean response time for all non-cell phone users, population 2. So what do we always do? We state the null and the alternative hypotheses first, and we'll start with the alternative. And clearly, we were testing if the mean mu, which is the mean response time for all cell phone users for the first group, population 1, is what? Greater, right? Greater than, that's the greater than sign, then the second group, right? So mu1 is greater than mu2, and you can also, like I said before, you can write it as the difference between the two. We go back to the null. Null always has equal to, right? So basically mu1 is equal to mu2, meaning there's no difference, alternative difference. Null hypothesis, no effect, nothing there. There is something there in the alternative. That's usually how it's always set up. Okay. Here's our output again, because we're going to need it for like conditions and stuff like that. And so conditions, we had an experiment. Hey, this was the first time we actually ran an experiment, because most of the time we've just been saying, hey, we had a random sample. Here we actually had an experiment. So remember, experiments are randomized. Remember that as the participants came in, they were randomly selected into the different groups. Okay, and then since n1 and n2 are both greater than or equal to 30, here's n1. Here's n2. They're both greater than or equal to 30. The central limit theorem applies. What does that mean? That the sampling distribution of x bar 1 minus x bar 2 will follow what? An approximately normal distribution, which is a t distribution, right? And so if the central limit theorem can apply, that means that we would have had to assume that the that the driver's reaction time, or the reaction time for the two groups, were both normal. Okay, so here we might see that in the second example, but for right now we'll just say that the central limit theorem applies and we're good. 3. Test stat. So here's our test stat again. Now you could put all the numbers in there, and so here's x bar 1 minus x bar 2. You could probably just put in that entire number instead of doing the difference. And remember, this value right here is always going to turn into 0, because that's the value in the null hypothesis. And then you can put in 89.6, square it, divided by 32, add 65.3, square it, divided by 32, do the whole square root thing, and you're basically going to come out this 2.63. Now remember, the computer has a bunch of decimal places stored, and so we're going to have a little bit of rounding error compared to the computer, because it only gave us our standard deviations to one decimal place, and our x bar 1 minus x bar 2 to 4 decimal places, but we should basically get 2.63. You don't have to, but if you wanted to, you can kind of confirm that. That's basically what you get, and there you go. Okay. P-value. P-value is what? 0.006. Okay. Okay, so here's all the information, and what would be our conclusion now? Our conclusion, well, okay, so what do we always do? We always compare our p-value to alpha. Alpha was set to 5%. Remember, that would mean that that's being set to 0.05. Okay, and so p-value less than alpha. What are we going to do? We're going to reject the null. And what does that mean? We have strong evidence that, so we have statistically significant evidence, we have sufficiently strong evidence that that the mean response time for all cell phone users is greater than that for all the non-cell phone users. So it looks like their reaction time was impaired because they had a longer average reaction time. All right. It looked like there was a big enough difference between x bar 1 and x bar 2 that we could now apply it to what? The entire populations, that there's a difference in the entire populations. So what are we saying is that because the difference between x bar 1 and x bar 2 was far enough apart, okay, and based upon standard errors, number of standard errors away, that mu1 is greater than mu2, and that's all we're stating here. We have strong evidence that the mean response time for all cell phone users, mu1, is greater than mu2. Okay, how about if we ran a confidence interval? Now we know what the hypothesis test told us, okay? Let's see what the confidence interval tells us. So let's say that we conducted a 95% confidence interval. All right, so that means we're going to be looking at this right here. And I'll just say that I know what's going to be on the next slide. Basically, I rounded this off to 2 decimal places, so you're going to see our confidence interval go from 12.24 to what? 90.80, because I rounded properly to 2 decimal places. So you'll see that. So there's our confidence interval, okay? And remember, this is not mu1, that's not mu1, that's not mu2. What is this for? This is the difference between mu1 and mu2. Okay, this is an estimate for that difference. So notice our entire confidence interval is what? Positive. It doesn't cross the value of 0. It doesn't have any negative values in it. Okay? So remember what I told you in the last video, that if your confidence interval is entirely positive, that what? Mu1 is what? Has to be greater than mu2. Alright? And that's exactly what we found with our hypothesis test. So I will tell you this, that whatever you found for your confidence interval, your hypothesis test is going to tell you exactly the same thing, and vice versa. So remember what our hypothesis test told us. Told us that mu1 is what? Greater than mu2. That's what we should expect then for our confidence interval. Okay? That our confidence interval is entirely positive and it's telling us that mu1 is greater than mu2. So here's our interpretation. We're 95% confident that the mean response time for all cell phone users is greater than that for all cell phone users. Same idea, but the confidence interval is actually telling us a little bit more. Why? Because it's telling us how much of a difference there is. Okay, so it's telling us that there's that big of a difference. Okay, and so the confidence interval now known is going to be consistent with the hypothesis test. It's going to tell us how much of a difference there is. Okay, so we think there's a difference between 12.24 and 90.8. Okay, so there's our first example. Let's go through a second example. Male versus female driving speeds. Ooh, now people get all bummed out by all this wording here, and don't. We're gonna break it down sentence by sentence here. An insurance company wants to know if the average speed time at which men drive cars is different than that of women drivers. So a random sample of 18 cars driven by women, so we're making women population 1, on a highway gave a mean speed to be 68 miles per hour with the standard deviation 2.5. And so here, instead of synthesizing the data with a table, okay, here we're just writing it out in words, and you will have to probably do both for homework and potentially on the exam. Okay, so don't freak out, you just got to organize. Okay, so here's population 1, women. What is this? We took a sample of 18 cars that were driven by women. So what would that be? That would be what? N1, right? Mean speed, that would be X bar 1, 68. Standard deviation, that would be S1. Okay, that's all we're trying to do. We're trying to get you to organize the data now based upon the wording. Okay, so another random sample of 27 cars driven by men, that would be population 2 on the same highway, gave a mean, so that must be N2, that 27. Gave a mean speed of 72. That's X bar 2. Standard deviation at 2.2, that would be S2. So that's really the bulk of the problem, is just organizing N1, X bar 1, S1, N2, X bar 2, S2. That's all. Tested the 5% significance level, that's alpha. Whether the mean speed of cars driven by all women drivers on this highway is different. What does that sound like? Or it sounds like a detailed test that we're going to be putting a not equal to sign into the alternative when we run a hypothesis test. Assume the speeds at which men and women drive cars on this highway are both normal. So because our sample size aren't greater than or equal to 30, we're going to have to go ahead and say that in our problem. Okay, so we have that in our conditions. So just like I said before, all we're doing is organizing the stuff. And so we had a random sample, 18 and 1, X bar 1, 68, okay, S1, 2.5, X bar 2, excuse me, is 72, okay, S2, 2.2, and then N2 looks like 27. Okay, so here's a StatCrunch output. 2-sample t-test, all right, and so sample difference, what is this? This is X bar 1 minus X bar 2 now. So like I said, that's a pretty important number, and it went ahead and gave us that value of a -4. So what does that mean? Based upon the samples, there was a miles per hour for a Ford difference, right? 4 mile per hour difference, and it looks like X bar 2 was greater than X bar 1. But is that a big enough difference to apply it to the entire population, knowing that we only had a sample size of that were fairly small? Okay, so here's a standard error. It's already been calculated for us. That would be that big old square root stuff. Degrees of freedom. Notice actually the degrees of freedom actually turn into a bunch of decimals. Minitab dropped the decimals. Basically, we have 33 degrees of freedom. I don't want to get into why the decimals afterwards just get dropped, but trust me on this, it's 33 degrees of freedom. Here's our test statistic, okay, and it turned out to be a negative 5.51. Boy, that's a big test stat, right? Magnitude, right? And which led to a very, very small p-value of 0.0001. Okay, actually less than that even. Okay, so state the hypotheses. Mu1 is not equal to mu2, right? We already talked about that we were testing that we had a two-tailed test, and so we have a not equal to sign in the alternative. Null hypothesis equal to sign. Hopefully that makes sense. So we have a two-tailed test. What does that mean? We are testing both greater than and less than at exactly the same time. Conditions. 2 independent random samples. Okay, we're going to we don't have the experiment anymore, but we do have 2 independent random samples. We have these 2 groups, and so the men and the women that we went ahead and sampled, they have nothing in common, so they're independent of one another. Since the sample size are both less than 30, we need to have an assumption that the speeds for both males and females are normal. That's what this last sentence is for. Okay. All right. 3. Test stat turned out to be a negative 5.51. 4. P-value extremely small. I mean immensely small, right? So the conclusion, so what that means is that we're going to reject the null hypothesis. That means we have strong evidence at the 5% significance level that the mean speed all women drive on this highway is different than that for all men. Okay, that's what the alternative was. Sound okay to you guys? All right, because the p-value is less than alpha, right? It's extremely small. We're going to reject the null. The null said they were equal to. The alternative said that they were different. This is an acceptable conclusion, but there's even a better conclusion here. Would you agree if I told you that something was different, that means either mu1 was less than mu2 or mu1 was greater than mu2? Okay? It's got to be one or the other. It can't be both. It's got to be either that mu1 was less than mu2 or mu1 was greater than mu2. Okay? So, so essentially we should be able to figure that out. Okay, so even though this is a reasonable conclusion, we can actually take it one step further and say, okay, which one was it? And so basically, who drove faster, the males or the females? If we picked up on a difference, well, we should be able to figure that out. Okay, and so let's see here. How's this? Why don't you pause the video, go back to what X bar 1 was telling you, what X bar 2 was telling you, and see if you can figure it out. Okay, if you can't figure it out, let's run through the conference, and the conference will definitely tell us. Okay, and we'll bring it all together after that. See if you could figure it out by looking at X bar 1 versus X bar 2. Okay, who was driving faster? Who we think was driving faster on average for the entire populations? Okay, so here, now I gave you interpreted 95% confidence interval, okay? And so here, look at the confidence interval. It's entirely... Now, with StatCrunch, I'll just tell you this, is that you will not get output for both the hypothesis test and the confidence interval at exactly the same time. You have to run the hypothesis test, and then if you want the confidence interval stuff, you got to run a separate test, essentially. You can't do it all in one shot, okay, where you did that in Minitab, okay? So here our confidence interval goes from a negative 5.48 if we rounded, and a negative 2.52. Okay, it's entirely negative. Okay, and let's see, so since the entire confidence interval is negative, we can infer what? Mu1 is what? Less than mu2. Mu2 is the greater number. Remember, this is certainly not mu1. This is certainly not mu2. This is the difference between mu1 and mu2. And if we have an entirely negative confidence interval, that's telling us what? Mu1 is less than mu2, or if you prefer, mu2 is greater than mu1. However you want to think of it. Okay? And it tells us by how much of a difference there is. So interpretation, we're 95% confident that the mean speed all women drive, all women car drivers, this should be drivers, on this highway is less than that for all males, anywhere from, and so students get a little confused. They want to put the negative sign here, but we would drop the negative sign because we already said it was less than. Okay, you wouldn't say less than a -2. You would just say something is so for instance, you had the numbers 3 and 5. Okay, you would say 3 is 2 units less than 5. You would not say 3 is -2 units less than 5. That does not make sense. Okay, so basically once we said less than, you get to drop these signs here, and they get flipped then, because you want to read this as, for smaller number first, larger number second. Hopefully that makes sense. Okay, and so notice here who had the who was driving quicker, faster on average for the entire populations? Males, right? And we can see that, and I'll back it up here. Where can we see that, right? So here was X bar 1 was 68, X bar 2 72, and so if we saw a difference in the hypothesis test, well, what's going to tell us which one is greater, mu1 or mu2? Well, we look at X bar 1 versus X bar 2. Okay, and X bar 2 was greater. Okay, so hopefully that that goes through everything for you. I don't think I have any more I do have one more slide. Okay, so we are done with this problem though. Okay, we are done with this problem. I have here pretend for the last, so pretend this is not what happened. Okay, but just pretend for the last example that the p-value turned out to be 0.2368, and certainly that would be greater than alpha of 0.05. And what would we say in that situation if this was the case? We would have said, do not reject the null, and we do not have strong evidence, right? Remember, the nots go together. When you say do not reject the null, we do not have strong evidence that the mean speed all women drive on this highway is significantly different than that for all men if the p-value was 0.2368. Okay, so I'm just giving you an example of what would happen if the p-value was greater than alpha. Now, what would we expect for our confidence interval then? Can you guys think it through? What are we going to expect? An entirely positive, entirely negative, or are we going to expect a confidence interval that crosses the value of 0? Hopefully you say that we're going to have a confidence interval that crosses the value of 0, that you have a negative here and a positive here. Because why? That's telling us that it's possible that 0 could be the difference between the two. And if 0 is a possibility for the difference between the two, there's a possibility that there's no difference. And so that's what we would expect. Okay, so the confidence interval contains the value of 0, and it is possible that the two population mean values are equal to one another. So both, when I say both, I mean both the confidence interval and the hypothesis test are indicating what? Inconclusive results. It could be that mu1 is greater than mu2, it could be that mu1 is less than mu2, it could be that mu1 is equal to mu2, and we don't know which one it is. Okay, and both, remember what I told you before, the hypothesis test and the confidence interval should be telling us exactly the same thing in the end. Okay, as far as, is mu1 greater than mu2, or is it less than, or is it not equal to, or if we can't tell the difference, both will tell you exactly the same results. All right, now if you notice, if you go back to the first two problems, notice we rejected the null hypothesis in both of those. what's going to happen then is that your confidence interval will either be entirely negative or entirely positive in that situation. So when you reject a null, what's going to happen with the confidence intervals is either going to be entirely negative or entirely positive. When you do not reject the null, what's going to happen with the confidence interval is going to be something like this, where it includes the value of 0. This is just saying that we're always going to have consistent results between the two. Okay. There we go. And with regards to not rejecting the null. All right. I think that ends the presentation. Got any questions? Let me know.